A clock is an instrument to indicate, keep, and coordinate time. The word clock is derived ultimately via Dutch, Northern French, and medieval Latin from the Celtic words claggen and clock meaning bell. A silent instrument missing such a mechanism has traditionally been known as a timepiece. In general usage today, a clock refers to any device for measuring and displaying the time. Watches and other timepieces that can be carried on one's person are often distinguished from clocks. The clock is one of the oldest human inventions, meeting the need to consistently measure intervals of time shorter than the natural units, the day, the lunar month, and the year. Devices operating on several physical processes have been used over the millennia. The evolution of the technology of clocks continues today. Simple horizontal sundial. When the sun is shining, its apparent position in the sky moves during a day, reflecting the rotation of the earth. Shadows cast by stationary objects move correspondingly, so their positions can be used to indicate the time of day. A sundial shows the time by displaying the position of a shadow on a, usually, flat surface, which has markings that correspond to the hours. Sundials can be horizontal, vertical, or in other orientations. Sundials were widely used in ancient times. With the knowledge of latitude, a well-constructed sundial can measure local solar time with reasonable accuracy, within a minute or two. Sundials continued to be used to monitor the performance of clocks until the modern era. However, practical limitations, such as that sundials work only when the sun shines and never during the night, encourage the use of other techniques for measuring and displaying time. Many devices can be used to mark passage of time without respect to reference time, time of day, minutes, etc., and can be useful for measuring duration and or intervals. Examples of such duration timers are candle clocks, incense clocks, and the hourglass. Both the candle clock and the incense clock work on the same principle, wherein the consumption of resources is more or less constant, allowing reasonably precise and repeatable estimates of time passages. In the hourglass, fine sand pouring through a tiny hole at a constant rate indicates an arbitrary, predetermined passage of time. The resource is not consumed but reused. Water clocks. Water clocks, also known as clepsydrae, clepsydra, along with the sundials, are possibly the oldest time-measuring instruments, with the only exceptions being the vertical gnomon and the day-counting tally stick. Given their great antiquity, where and when they first existed is not known, and perhaps unknowable. The bowl-shaped outflow is the simplest form of a water clock, and is known to have existed in Babylon and in Egypt around the 16th century BC. Other regions of the world, including India and China, also have early evidence of water clocks, but the earliest dates are less certain. Some authors, however, write about water clocks appearing as early as 4000 BC in these regions of the world. Greek astronomer Andronicius of Cyrrhus supervised the construction of the Tower of the Winds in Athens in the 1st century BC. The Greek and Roman civilizations are credited for initially advancing water clock design to include complex gearing, which was connected to fanciful automata and also resulted in improved accuracy. These advances were passed on through Byzantium and Islamic times, eventually making their way back to Europe. Independently, the Chinese developed their own advanced water clocks in 725 AD, passing their ideas on to Korea and Japan. Automatic clock of Al-Jazari, 14th century. Some water clock designs were developed independently, and some knowledge was transferred through the spread of trade. Pre-modern societies do not have the same precise timekeeping requirements that exist in modern industrial societies, where every hour of work or rest is monitored, and work may start or finish at any time regardless of external conditions. Instead, water clocks in ancient societies were used mainly for astrological reasons. These early water clocks were calibrated with a sundial. While never reaching the level of accuracy of a modern timepiece, The water clock was the most accurate and commonly used timekeeping device for millennia until it was replaced by the more accurate pendulum clock in 17th century Europe. Islamic civilization is credited with further advancing the accuracy of clocks with elaborate engineering. In 797, or possibly 801, the Abbasid Caliph of Baghdad, Harun al-Rashid, presented Charlemagne with an Asian elephant named Abu Labis together with a particularly elaborate example of a water clock. Pope Sylvester II introduced clocks to northern and western Europe, around 1000 CE. An elephant clock in a manuscript by Al-Jazari, 1206 AD, from the Book of Knowledge of Ingenious Mechanical Devices. In the 13th century, Al-Jazari, an engineer from Mesopotamia, lived 1136 to 1206, who worked for Archukid king of Diyarbakir, Nasir al-Din, made numerous clocks of all shapes and sizes. The book described 50 mechanical devices in 6 categories, including water clocks. The most reputed clocks included the elephant, scribe, and castle clocks, all of which have been successfully reconstructed. As well as telling the time, these grand clocks were symbols of status, grandeur, and wealth of the heir to state. Early mechanical clocks. The word horologia, from the Greek hour and to tell, was used to describe early mechanical clocks, but the use of this word, still used in several Romance languages, for all timekeepers conceals the true nature of the mechanisms. For example, there is a record that in 1176 Sens Cathedral installed a horologe, but the mechanism used is unknown. According to Jocelyn of Brakelond, in 1198, during a fire at the Abbey of St. Edmundsbury, now Bury St. Edmunds, the monks ran to the clock to fetch water, indicating that their water clock had a reservoir large enough to help extinguish the occasional fire. The word clock, from the Celtic words cloch and clogan, both meaning bell which gradually supersedes horologe, suggests that it was the sound of bells which also characterized the prototype mechanical clocks that appeared during the 13th century in Europe. Outside Europe, the first mechanical clock was completed in China in AD 725 by Yixing and Liang Lingzan. The escapement mechanism had been known and used in medieval China, as the Song dynasty horologist and engineer Su Song, 1020-1101, incorporated it into his astronomical clock tower of Kaifeng, in 1088. Page needed his astronomical clock, and rotating armillary sphere still relied on the use of flowing water, i.e. hydraulics, while European clockworks of the following centuries shed this method for a more efficient driving power of weights, in addition to the escapement mechanism. A mercury clock, described in the Libros del Saber, a Spanish work from 1277 consisting of translations and paraphrases of Arabic works, is sometimes quoted as evidence for Muslim knowledge of a mechanical clock. The first mercury-powered automata clock was invented by Ibn Khalaf al-Muradi. Between 1280 and 1320, there is an increase in the number of references to clocks and horologes in church records, and this probably indicates that a new type of clock mechanism had been devised. Existing clock mechanisms that used water power were being adapted to take their driving power from falling weights. This power was controlled by some form of oscillating mechanism, probably derived from existing bell ringing or alarm devices. This controlled release of power, the escapement, marks the beginning of the true mechanical clock. These mechanical clocks were intended for two main purposes: for signaling and notification, e.g. the timing of services and public events, and for modeling the solar system. The former purpose is administrative, the latter arises naturally given the scholarly interest in astronomy, science, astrology, and how these subjects integrated with the religious philosophy of the time. The astrolabe was used both by astronomers and astrologers, and it was natural to apply a clockwork drive to the rotating plate to produce a working model of the solar system. Simple clocks intended mainly for notification were installed in towers, and did not always require faces or hands. They would have announced the canonical hours or intervals between set times of prayer. Canonical hours varied in length as the times of sunrise and sunset shifted. The more sophisticated astronomical clocks would have had moving dials or hands, and would have shown the time in various time systems, including Italian hours, canonical hours, and time, as measured by astronomers at the time. Both styles of clock started acquiring extravagant features such as automata. In 1283, a large clock was installed at Dunstable Priory. Its location, above the rood screen, suggests that it was not a water clock. In 1292, Canterbury Cathedral installed a great horologe. Over the next 30 years there are mentions of clocks at a number of ecclesiastical institutions in England, Italy, and France. In 1322, a new clock was installed in Norwich, an expensive replacement for an earlier clock installed in 1273. This had a large, 2-meter, astronomical dial with automata and bells. The costs of the installation included the full-time employment of 2 clock keepers for 2 years. Astronomical clocks. Richard of Wallingford pointing to a clock, his gift to St. Albans Abbey. Besides the Chinese astronomical clock of Susong in 1088 mentioned above, in Europe, there were the clocks constructed by Richard of Wallingford in St. Albans, by 1336, and by Giovanni da Dondi in Padua, from 1348 to 1364. They no longer exist, but detailed descriptions of their design and construction survive, and modern reproductions have been made. They illustrate how quickly the theory of the mechanical clock had been translated into practical constructions, and also that one of the many impulses to their development had been the desire of astronomers to investigate celestial phenomena. Wallingford's clock had a large astrolabe-type dial, showing the sun, the moon's age, phase, and node, a star map, and possibly the planets. In addition, it had a wheel of fortune, and an indicator of the state of the tide at London Bridge. Bells rang every hour, the number of strokes indicating the time. Dondi's clock was a 7-sided construction, 1 meter high, with dials showing the time of day, including minutes, the motions of all the known planets, an automatic calendar of fixed and movable feasts, and an eclipse prediction hand rotating once every 18 years. It is not known how accurate or reliable these clocks would have been. They were probably adjusted manually every day to compensate for errors caused by wear and imprecise manufacture. Water clocks are sometimes still used today, and can be examined in places such as ancient castles and museums. The Salisbury Cathedral clock, built in 1386, is considered to be the world's oldest surviving mechanical clock that strikes the hours. Spring-driven clocks. One of the first pocket watches, called Nuremberg Egg, made around 1510, and attributed to Peter Henlein, Germanisches National Museum, Nuremberg. Clockmakers developed their art in various ways. Building smaller clocks was a technical challenge, as was improving accuracy and reliability. Clocks could be impressive showpieces, to demonstrate skilled craftsmanship, or less expensive, mass-produced items for domestic use. The escapement in particular was an important factor affecting the clock's accuracy. So many different mechanisms were tried. Spring-driven clocks appeared during the 15th century, although they are often erroneously credited to Nuremberg watchmaker Peter Henlein, or Henley, or Heel, around 1511. The earliest existing spring-driven clock is the chamber clock given to Philip the Good, Duke of Burgundy, around 1430, now in the Germanisches National Museum. Spring power presented clockmakers with a new problem: how to keep the clock movement running at a constant rate as the spring ran down. This resulted in the invention of the Stackfried and the fusee in the 15th century, and many other innovations, down to the invention of the modern going barrel, in 1760. Early clock dials did not indicate minutes and seconds. A clock with a dial indicating minutes was illustrated in a 1475 manuscript by Paulus Salmanus. And some 15th century clocks in Germany indicated minutes and seconds. An early record of a seconds hand on a clock dates back to about 1560 on a clock now in the Fremersdorf collection. However, this clock could not have been accurate, and the seconds hand was probably for indicating that the clock was working. During the 15th and 16th centuries, clockmaking flourished, particularly in the metalworking towns of Nuremberg and Augsburg, and in Blois, France. Some of the more basic table clocks have only one timekeeping hand, with the dial between the hour markers being divided into 4 equal parts, making the clocks readable to the nearest 15 minutes. Other clocks were exhibitions of craftsmanship and skill, incorporating astronomical indicators and musical movements. The crossbeat escapement was invented in 1584 by Juste Bourget, who also developed the remontoire. Bourget's clocks were a great improvement in accuracy, as they were correct to within a minute a day. These clocks helped the 16th century astronomer Tycho Brahe to observe astronomical events with much greater precision than before. French Rococo bracket clocks, Museum of Time, Besançon. Pendulum clock. The next development in accuracy occurred after 1656, with the invention of the pendulum clock. Galileo had the idea to use a swinging bob to regulate the motion of a time-telling device earlier in the 17th century. Christian Huygens, however, is usually credited as the inventor. He determined the mathematical formula that related pendulum length to time, 99.38 centimeters, or 39.13 inches for the 1-second movement, and had the first pendulum-driven clock made. The first model clock was built in 1657, in The Hague, but it was in England that the idea was taken up. The long case clock, also known as the grandfather clock, was created to house the pendulum and works by the English clockmaker William Clement in 1670 or 1671. It was also at this time that clock cases began to be made of wood and clock faces to utilize enamel as well as hand-painted ceramics. In 1670, William Clement created the anchor escapement, an improvement over Huygens' crown escapement. Clement also introduced the pendulum suspension spring in 1671. The concentric minute hand was added to the clock by Daniel Quare, a London clockmaker, and others, and the second hand was first introduced. The hairspring. In 1675, Huygens and Robert Hooke invented the spiral balance, or the hairspring, designed to control the oscillating speed of the balance wheel. This crucial advance finally made accurate pocket watches possible. The great English clockmaker, Thomas Dompion, was one of the first to use this mechanism successfully in his pocket watches, and he adopted the minute hand which, after a variety of designs were trialed, eventually stabilized into the modern-day configuration. The Reverend Edward Barlow invented the rack and snail striking mechanism for striking clocks, which was a great improvement over the previous mechanism. The repeating clock, that chimes the number of hours, or even minutes, was invented by either Quare or Barlow in 1676. George Graham invented the deadbeat escapement for clocks in 1720. Marine chronometer. Drawings of Harrison's H4 chronometer of 1761, published in the Principles of M. R. Harrison's Timekeeper, 1767. A major stimulus to improving the accuracy and reliability of clocks was the importance of precise timekeeping for navigation. The position of a ship at sea could be determined with reasonable accuracy if the navigator could refer to a clock that lost or gained less than about 10 seconds per day. This clock could not contain a pendulum, which would be virtually useless on a rocking ship. The British government offered a large prize to the value of £20,000 for anyone who could determine longitude accurately after the Scilly naval disaster of 1707. The reward was eventually claimed in 1761 by John Harrison, who dedicated his life to improving the accuracy of his clocks. John Harrison's chronometer H5. In 1735 Harrison built his first chronometer, which he steadily improved on over the next 30 years, before submitting it for examination. The clock had many innovations, including the use of bearings to reduce friction, weighted balances to compensate for the ship's pitch and roll in the sea, and the use of 2 different metals to reduce the problem of expansion from heat. The chronometer was tested in 1761 by Harris and Son, and by the end of 10 weeks the clock was in error by less than 5 seconds. Mass production. The British had predominated in watch manufacture for much of the 17th and 18th centuries, but maintained a system of production that was geared towards high-quality products for the elite. Although there was an attempt to modernize clock manufacture with mass production techniques and the application of duplicating tools and machinery by the British Watch Company in 1843, it was in the United States that the system took off. Aaron Lufkin Denison started a factory in 1851 in Massachusetts that used interchangeable parts, and by 1861 was running a successful enterprise incorporated as the Waltham Watch Company. Electric clocks. Alexander Bain, Scottish clockmaker, patented the electric clock in 1840. The electric clock's mainspring is wound either with an electric motor or with an electromagnet and armature. In 1841, he first patented the electromagnetic pendulum. By the end of the 19th century, the advent of the dry cell battery made it feasible to use electric power in clocks. Spring or weight-driven clocks that use electricity, either alternating current, AC, or direct current, DC, to rewind the spring or raise the weight of a mechanical clock would be classified as an electromechanical clock. This classification would also apply to clocks that employ an electrical impulse to propel the pendulum. In electromechanical clocks, the electricity serves no timekeeping function. These types of clocks were made as individual timepieces, but more commonly used in synchronized time installations in schools, businesses, factories, railroads, and government facilities, as a master clock and slave clocks. Electric clocks that are powered from the AC supply often use synchronous motors. The supply current alternates with a frequency of exactly 50 Hz in many countries and 60 Hz in others. The rotor of the motor rotates at a speed that is exactly related to the alternation frequency. Appropriate gearing converts this rotation speed to the correct ones for the hands of the analog clock. The development of electronics in the 20th century led to clocks with no clockwork parts at all. Time in these cases is measured in several ways, such as by the alternation of the AC supply, vibration of a tuning fork, the behavior of quartz crystals, or the quantum vibrations of atoms. Electronic circuits divide these high-frequency oscillations to slower ones that drive the time display. Even mechanical clocks have since come to be largely powered by batteries, removing the need for winding. How clocks work. The invention of the mechanical clock in the 13th century initiated a change in timekeeping methods from continuous processes, such as the motion of the gnomons shadow on a sundial, or the flow of liquid in a water clock, to periodic oscillatory processes, such as the swing of a pendulum, or the vibration of a quartz crystal, which had the potential for more accuracy. All modern clocks use oscillation. Although the methods they use vary, all oscillating clocks, mechanical and digital and atomic, work similarly and can be divided into analogous parts. They consist of an object that repeats the same motion over and over again, an oscillator with a precisely constant time interval between each repetition, or beat. Attached to the oscillator is a controller device, which sustains the oscillator's motion by replacing the energy it loses to friction, and converts its oscillations into a series of pulses. The pulses are then counted by some type of counter, and the number of counts is converted into convenient units, usually seconds, minutes, hours, etc. Finally, some kind of indicator displays the result in human-readable form. Power source. Keys of various sizes for winding up mainsprings on clocks. This provides power to keep the clock going. In mechanical clocks, the power source is typically either a weight suspended from a cord or chain wrapped around a pulley, sprocket, or drum, or a spiral spring called a mainspring. Mechanical clocks must be wound periodically, usually by turning a knob or key, or by pulling on the free end of the chain, to store energy in the weight or spring to keep the clock running. In electric clocks, the power source is either a battery or the AC power line. In clocks that use AC power, a small backup battery is often included to keep the clock running if it is unplugged temporarily from the wall, or during a power cut. Oscillator. The timekeeping element in every modern clock is a harmonic oscillator, a physical object, resonator, that vibrates, or oscillates repetitively at a precisely constant frequency. In mechanical clocks, this is either a pendulum, or a balance wheel. In some early electronic clocks and watches such as the Accutron, it is a tuning fork. In quartz clocks and watches, it is a quartz crystal. In atomic clocks, it is the vibration of electrons in atoms as they emit microwaves. In early mechanical clocks, before 1657, it was a crude balance wheel or foliot which was not a harmonic oscillator because it lacked a balance spring. As a result, they were very inaccurate, with errors of perhaps an hour a day. The advantage of a harmonic oscillator over other forms of oscillator is that it employs resonance to vibrate at a precise natural resonant frequency, or beat, dependent only on its physical characteristics, and resists vibrating at other rates. The possible precision achievable by a harmonic oscillator is measured by a parameter called its Q, or quality factor, which increases, other things being equal, with its resonant frequency. This is why there has been a long-term trend toward higher frequency oscillators in clocks. Balance wheels and pendulums always include a means of adjusting the rate of the timepiece. Quartz timepieces sometimes include a rate screw that adjusts a capacitor for that purpose. Atomic clocks are primary standards, and their rate cannot be adjusted. Synchronized or slave clocks. Some clocks rely for their accuracy on an external oscillator, that is, they are automatically synchronized to a more accurate clock. Slave clocks, used in large institutions and schools from the 1860s to the 1970s, kept time with a pendulum, but were wired to a master clock in the building, and periodically received a signal to synchronize them with the master, often on the hour. Later versions without pendulums were triggered by a pulse from the master clock, and certain sequences used to force rapid synchronization following a power failure. Synchronous electric clocks do not have an internal oscillator, but count cycles of the 50 or 60 Hz oscillation of the AC power line, which is synchronized by the utility to a precision oscillator. The counting may be done electronically, usually in clocks with digital displays, or, in analog clocks, the AC may drive a synchronous motor which rotates an exact fraction of a revolution for every cycle of the line voltage, and drives the gear train. Although changes in the grid line frequency due to load variations may cause the clock to temporarily gain or lose several seconds during the course of a day, the total number of cycles per 24 hours is maintained extremely accurately by the utility company, so that the clock keeps time accurately over long periods. Computer real-time clocks keep time with a quartz crystal, but can be periodically, usually weekly, synchronized over the Internet to atomic clocks, UTC, using the Network Time Protocol, NTP. Sometimes computers on a local area network, LAN, get their time from a single local server which is maintained accurately. Radio clocks keep time with a quartz crystal, but are periodically synchronized to time signals transmitted from dedicated standard time radio stations or satellite navigation signals, which are set by atomic clocks. Controller. This has the dual function of keeping the oscillator running by giving it pushes to replace the energy lost to friction, and converting its vibrations into a series of pulses that serve to measure the time. In mechanical clocks, this is the escapement, which gives precise pushes to the swinging pendulum or balance wheel, and releases one gear tooth of the escape wheel at each swing, allowing all the clock's wheels to move forward a fixed amount with each swing. In electronic clocks, this is an electronic oscillator circuit that gives the vibrating quartz crystal or tuning fork tiny pushes, and generates a series of electrical pulses, one for each vibration of the crystal, which is called the clock signal. In atomic clocks, the controller is an evacuated microwave cavity attached to a microwave oscillator controlled by a microprocessor. A thin gas of cesium atoms is released into the cavity, where they are exposed to microwaves. A laser measures how many atoms have absorbed the microwaves, and an electronic feedback control system called a phase-locked loop tunes the microwave oscillator until it is at the exact frequency that causes the atoms to vibrate and absorb the microwaves. Then the microwave signal is divided by digital counters to become the clock signal. In mechanical clocks, the low Q of the balance wheel or pendulum oscillator made them very sensitive to the disturbing effect of the impulses of the escapement, so the escapement had a great effect on the accuracy of the clock, and many escapement designs were tried. The higher Q of resonators in electronic clocks makes them relatively insensitive to the disturbing effects of the drive power, so the driving oscillator circuit is a much less critical component. Counter chain. This counts the pulses and adds them up to get traditional time units of seconds, minutes, hours, etc. It usually has a provision for setting the clock by manually entering the correct time into the counter. In mechanical clocks this is done mechanically by a gear train, known as the wheel train. The gear train also has a second function, to transmit mechanical power from the power source to run the oscillator. There is a friction coupling called the cannon pinion between the gears driving the hands and the rest of the clock, allowing the hands to be turned to set the time. In digital clocks, a series of integrated circuit counters or dividers add the pulses up digitally, using binary logic. Often push buttons on the case allow the hour and minute counters to be incremented and decremented to set the time. Indicator. A cuckoo clock with mechanical automaton and sound producer striking on the 8th hour on the analog dial. This displays the count of seconds, minutes, hours, etc. in a human-readable form. The earliest mechanical clocks in the 13th century didn't have a visual indicator and signaled the time audibly by striking bells. Many clocks to this day are striking clocks which strike the hour. Analog clocks display time with an analog clock face, which consists of a round dial with the numbers 1 through 12, the hours in the day, around the outside. The hours are indicated with an hour hand, which makes 2 revolutions in a day, while the minutes are indicated by a minute hand, which makes 1 revolution per hour. In mechanical clocks a gear train drives the hands. In electronic clocks the circuit produces pulses every second which drive a stepper motor and gear train, which move the hands. Digital clocks display the time in periodically changing digits on a digital display. Talking clocks and the speaking clock services provided by telephone companies speak the time audibly, using either recorded or digitally synthesized voices. Types. Clocks can be classified by the type of time display, as well as by the method of timekeeping. Time display methods. Analog clocks. A linear clock at London's Piccadilly Circus tube station. The 24-hour band moves across the static map, keeping pace with the apparent movement of the sun above ground, and a pointer fixed on London points to the current time. Analog clocks usually indicate time using angles. The most common clock face uses a fixed numbered dial or dials, and moving hand or hands. It usually has a circular scale of 12 hours, which can also serve as a scale of 60 minutes and 60 seconds if the clock has a second hand. Many other styles and designs have been used throughout the years, including dials divided into 6, 8, 10, and 24 hours. The only other widely used clock face today is the 24-hour analog dial, because of their use of 24-hour time in military organizations and timetables. The 10-hour clock was briefly popular during the French Revolution, when the metric system was applied to time measurement, and an Italian 6-hour clock was developed in the 18th century, presumably to save power. A clock or watch striking 24 times uses more power. Another type of analog clock is the sundial, which tracks the sun continuously, registering the time by the shadow position of its gnomon. Because the sun does not adjust to daylight savings times, users must add an hour during that time. Corrections must also be made for the equation of time, and for the difference between the longitudes of the sundial and of the central meridian of the time zone that is being used, i.e. 15 degrees east of the prime meridian, for each hour that the time zone is ahead of GMT. Sundials use some or part of the 24-hour analog dial. There also exist clocks which use a digital display. Despite having an analog mechanism, these are commonly referred to as flipped clocks. Alternative systems have been proposed. For example, the 12 clock indicates the current hour using one of 12 colors, and indicates the minute by showing a proportion of a circular disc, similar to a moon phase. Digital clocks. Digital clock outside Kanazawa Station displaying the time by controlling valves on a fountain. Basic digital clock radio. Mobile phone display including two clocks, analog style, albeit generated by a digital computer, in the middle, and digital style, in the top right corner. Digital clocks display a numeric representation of time. Two numeric display formats are commonly used on digital clocks. The 24-hour notation with hours ranging 0023. The 12-hour notation with AM/PM indicator, with hours indicated as 12 a.m., followed by 1 a.m. 11 a.m., followed by 12 p.m., followed by 1 p.m. 11 p.m., a notation mostly used in domestic environments. Most digital clocks use electronic mechanisms and LCD, LED, or VFD displays. Many other display technologies are used as well, cathode ray tubes, Nixie tubes, etc. After a reset, battery change, or power failure, these clocks, without a backup battery or capacitor, either start counting from 12 o'clock, or stay at 12 o'clock, often with blinking digits indicating that the time needs to be set. Some newer clocks will reset themselves based on radio or internet time servers that are tuned to national atomic clocks. Since the advent of digital clocks in the 1960s, the use of analog clocks has declined significantly. Some clocks have digital displays, but work mechanically. The digits are painted on sheets of material which are often mounted, like the pages of a book. Once a minute, a page is turned over to reveal the next digit. These displays are usually easier to read in brightly lit conditions than LCDs or LEDs. Also, they do not go back to 12 o'clock after a power interruption. Auditory clocks. Talking clock for convenience, distance, telephony, or blindness. Auditory clocks present the time as sounds. The sound is either spoken natural language, e.g. the time is 12:35, or as auditory codes, e.g. number of sequential bell rings on the hour represents the number of the hour, like the bell Big Ben. Most telecommunication companies also provide a speaking clock service as well. Word clocks. Software word clock. Word clocks are clocks that display the time visually using sentences. E.g., it's about 3 o'clock. These clocks can be implemented in hardware or software. Projection clocks. Some clocks, usually digital ones, include an optical projector that shines a magnified image of the time display onto a screen, or onto a surface such as an indoor ceiling or wall. The digits are large enough to be easily read, without using glasses, by persons with moderately imperfect vision, so the clocks are convenient for use in their bedrooms. Usually, the timekeeping circuitry has a battery as a backup source for an uninterrupted power supply to keep the clock on time, while the projection light only works when the unit is connected to an AC supply. Completely battery-powered portable versions resembling flashlights are also available. Tactile clocks. Auditory and projection clocks can be used by people who are blind or have limited vision. There are also clocks for the blind that have displays that can be read by using the sense of touch. Some of these are similar to normal analog displays, but are constructed so the hands can be felt without damaging them. Another type is essentially digital, and uses devices that use a code such as Braille to show the digits so that they can be felt with the fingertips. Multi-display clocks. Some clocks have several displays driven by a single mechanism, and some others have several completely separate mechanisms in a single case. Clocks in public places often have several faces visible from different directions, so that the clock can be read from anywhere in the vicinity. Of course, all the faces show the same time. Other clocks show the current time in several time zones. Watches that are intended to be carried by travelers often have two displays, one for the local time and the other for the time at home, which is useful for making pre-arranged phone calls. Some equation clocks have two displays, one showing mean time and the other solar time, as would be shown by a sundial. Some clocks have both analog and digital displays. Clocks with braille displays usually also have conventional digits, so they can be read by sighted people. Purposes: clocks are in homes, offices and many other places. Smaller ones, watches, are carried on the wrist or in a pocket. Larger ones are in public places, e.g. a railway station or church. A small clock is often shown in a corner of computer displays, mobile phones, and many MP3 players. The primary purpose of a clock is to display the time. Clocks may also have the facility to make a loud alert signal at a specified time, typically to waken a sleeper at a preset time. They are referred to as alarm clocks. The alarm may start at a low volume and become louder, or have the facility to be switched off for a few minutes then resume. Alarm clocks with visible indicators are sometimes used to indicate to children too young to read the time that the time for sleep has finished. They are sometimes called training clocks. A clock mechanism may be used to control a device according to time, e.g. a central heating system, a VCR, or a time bomb, see counter. Such mechanisms are usually called timers. Clock mechanisms are also used to drive devices such as solar trackers and astronomical telescopes, which have to turn at accurately controlled speeds to counteract the rotation of the Earth. Most digital computers depend on an internal signal at constant frequency to synchronize processing. This is referred to as a clock signal. A few research projects are developing CPUs based on asynchronous circuits. Some equipment, including computers, also maintains time and date for use as required. This is referred to as time-of-day clock, and is distinct from the system clock signal, although possibly based on counting its cycles. Time standards. For some scientific work, timing of the utmost accuracy is essential. It is also necessary to have a standard of the maximum accuracy against which working clocks can be calibrated. An ideal clock would give the time to unlimited accuracy, but this is of course not realizable. Many physical processes, in particular including some transitions between atomic energy levels, occur at exceedingly stable frequency. Counting cycles of such a process can give a very accurate and consistent time. Clocks which work this way are usually called atomic clocks. Such clocks are typically large, very expensive, require a controlled environment, and are far more accurate than required for most purposes. They are typically used in a standards laboratory. Navigation. Until advances in the late 20th century, navigation depended on the ability to measure latitude and longitude. Latitude can be determined through celestial navigation. The measurement of longitude requires accurate knowledge of time. This need was a major motivation for the development of accurate mechanical clocks. John Harrison created the first highly accurate marine chronometer in the mid-18th century. The noon gun in Cape Town still fires an accurate signal to allow ships to check their chronometers. Many buildings near major ports used to have, some still do, a large ball mounted on a tower or mast arranged to drop at a predetermined time, for the same purpose. While satellite navigation systems such as the Global Positioning System, GPS, require unprecedentedly accurate knowledge of time, this is supplied by equipment on the satellites. Vehicles no longer need timekeeping equipment. Seismology. In determining the location of an earthquake, the arrival time of several types of seismic wave at a minimum of 4 dispersed observers is dependent upon each observer recording wave arrival times according to a common clock.